A, B, and C are positive integers, and the following is an attempted proof of the false statement: if A divides BC, then A divides B, or A divides C. And a good example, which I'm actually going to use later on, is, for example, A dividing 3 times 2. So if A is equal to 6, B equal to 2, C equals 3, then 6 divides 6, but 6 does not divide 2 and does not divide 3. So you can see that this is going to be a false statement. But we're asked here where to find the error in this proof, and it's quite subtle actually. Let's look through. So the statement is equivalent to if A does not imply B and A does not divide C, then A does not divide BC. Now this is the contrapositive, and they are equivalent statements. So if one statement is true, then the contrapositive is true, or if the statement's false, the contrapositive is false, and vice versa. So that is okay. And so that is now what we're equivalently trying to prove. So suppose A does not divide B and A does not divide C, then the remainder when dividing B by A is R, where R is between 0 and A, and the remainder when dividing C by A is S, where 0 is less than S, which is less than A. There's no problem with that. Yeah, we know that A does not divide B, so when we try and do it, we're going to get a remainder, and it's going to be greater than 0 but less than A. And that means we can write down B as some multiple of A plus a remainder, and C as some multiple of A plus a different remainder. Yeah, no problem with that either. And if you if you multiply them, then you get a double bracket, AX plus R times AY plus S, and you would get A squared XY plus AXS plus ARY plus RS. And you could factorize the A out of the first three to give you AXY plus XS plus RY. So yeah, that is all good. No problem with that algebraically. Then it says, so the remainder when dividing BC by A is RS. And when I first read this, I thought, yeah, okay, that doesn't seem to be a problem. But it must be, because everything else, like this seems to be okay, and this seems to be okay. So the problem is here, and our answer is going to be line 5. But why is that? Let's talk about it a little bit more. Just because the remainder for the first one was R and the second one was S doesn't actually mean the remainder is going to be RS. You don't necessarily multiply the remainders together because maybe A goes into RS. RS could be bigger than A. And that is basically, yeah, that is it. Actually, it could go into it entirely even. Um, so let's do an example to show that. Again, let's use this one here. So if I had 6, 2, and 3, then I can see that 2 is not divisible by 6. We would get 2 is equal to 0 times 6 plus my remainder of 2. And 3 is not divisible by 6. 3 equals 0 times 6 plus 3. So that is what I'm doing really with I've jumped straight to step 3. So then B times C, which is 2 times 3, would equal 6. 6 times 0 times 0 plus, what was it? 3 times, I'm sorry, I'm going to do this in full. So it's actually going to be this bracket, 0 times 6 plus 2 multiplied by 0 times 6 plus 3. And that is going to give me 0 times 0 times 6 times 6 plus 0 times 6 times 3 plus 0 times 6 times 2 plus 2 times 3. Right, I'm now going to go to that step where they factorized it. So they've taken a 6 out, and we've got 0 times 6 times 6 plus 0 times 3 plus 0 times 2 plus 6. Okay, that 6 is our RS, and what we are seeing in this example is, okay, RS might be greater than 0, but that doesn't mean that A doesn't divide BC, because A actually goes into this remainder. It didn't go into 2 and 3, but it does go into their product. So that is at the heart of why the proof fails. Hopefully that makes sense, and it's line 5 where it falls apart.